Good morning everyone. Welcome to the third lecture for Introduction to Stability. So before we go further, let's recap what we studied in the previous class. So far we have discussed different types of buckling based on load deformation relationship, which could be bifurcation buckling, limit point buckling, finite disturbance buckling, as well as snap-through buckling. Based on modes of failure, we have local buckling of plate, flexural buckling for doubly symmetric columns, we have torsional buckling for cruciform sections, we have flexural torsional buckling also known as FTB for singly symmetric columns, we also have lateral torsional buckling for beams also known as LTB, we have distortional buckling for beams with slender webs as well as buckling of the entire frame. So based on load deformation relationship, the first figure introduces bifurcation buckling, the second one is limit point buckling, the third one is finite disturbance buckling, and the fourth one is snap-through buckling for shallow arches. We also studied about equilibrium states. So stable is considered when a body returns to its equilibrium position. As such, you can see a picture on the right side which comes back to the original position. Unstable if the body continues to move farther away from the original equilibrium position, and as you can see from the picture on the right side. The third one is the neutral equilibrium if the body remains at the adjacent position. So stability talks about equilibrium state of the structure. The definition of stability has nothing to do with the change in geometry of the structure under compression. Now we will talk about spring bar models. It's an illustration of buckling. So before going into the study of stability of elastic structures, let us try to understand a simple mechanical model which is used for obtaining critical equilibrium conditions. Consider a rigid bar of length A hinged at one end and connected to a spring at the free end subjected to external loads P and M. So the picture on the left side shows you the required descriptions of the structure. So we have a rigid bar which is pinned at the bottom, free at the top, and it is connected to a spring K, and which again is connected to a roller which can slide vertically, and the axial load P is applied as well as a moment M is applied. The length of the bar is A. The question that arises now is, will the rigid bar be in upright position under the applied load P? To answer this, we must consider all possible deflection in the system. So in this system, there are three possible deflections. Rotation at the hinge end A, which is theta. As you can see on the right side, it can rotate at the end A by an angle theta. And then elongation of the spring at end B delta, small delta due to theta. You can also see that at the picture. And there is a restoring force that is due to the spring action, that there will be a restoring force which wants to come back to the equilibrium position. The third deflection is the vertical deflection of roller attached to spring, and which we call it as delta again, but this is capital delta. For loaded condition, recall the three necessary and sufficient conditions. First is the equilibrium condition. We are taking moment about point A, which is sigma MA. Here P into delta we are taking is clockwise positive, so P into delta plus M minus FA cos theta. A cos theta is the length of the reduced length of the bar because of the deflection theta. And then there is a stress strain relationship F equal to K delta, which is basically the spring action. And then there is strain displacement relationship, which is delta equal to A sin theta. So from delta and F, the equations 2 and 3, when it is substituted into equation 1, leads to the equilibrium equation P delta plus M minus FA cos theta equal to 0, which implies P delta equal to FA cos theta minus M. So this implies F into A sin theta equal to K delta into A cos theta minus M. PA sin theta equal to K into A sin theta into A cos theta minus M. So dividing both sides with A sin theta, so which gives you P equal to Ka cos theta minus M divided by A sin theta, which becomes equation 4a. Or we can also represent P by Ka equal to cos theta minus M slash Ka square divided by sin theta. So, equations 4a and 4b defines the equilibrium position by relating P and delta for a given moment m, for a given stiffness K and the length of the bar A. But how to know whether this equilibrium is in stable, unstable or neutral equilibrium? This can be achieved by using what is known as perturbation technique, which we have studied in the last class as well. So, what is perturbation technique? Perturbation technique is to perturb a structure which is already in equilibrium and then applying a small perturbation. If the structure can come back to the original position, it is stable. If it cannot come back to the original position and keeps moving, it is unstable. If it slightly displaces and stands still, then it is in neutral equilibrium. Here in this case, the deflected shape is having a displacement or a rotation theta. We are actually displacing it further by increasing it slightly by theta star. So, the total displacement or rotation here now is theta plus theta star, and the corresponding lateral displacement is delta dash. And the load P remains the same, the moment P remains the same. However, the restoring force is a function of the movement, which is delta dash. So, the restoring force is no longer F, it becomes F dash. So, taking moment here now, sigma ma equal to P delta dash plus m minus F dash a cos into theta plus theta star. By using the perturbation technique, we get the following equation: sigma ma equal to P delta dash plus m minus F dash a cos theta plus theta star equal to 0. By perturbation technique, we consider the perturbed position theta plus theta star, for which 1, 2 and 3 take the form 5, 6 and 7. The 5 is the equilibrium condition, which is sigma ma equal to P delta dash plus m minus F dash a cos theta plus theta star equal to 0. 6th equation is stress strain relationship F dash equal to K delta dash. Equation 7 basically is the strain displacement relationship delta dash equal to A sin theta plus theta star. So, substituting 7 and 6 in equation 5 leads to the following equation. This equation needs to be expanded. This is of the form sin A plus B as well as cos A plus B. We know from high school mathematics that sin A plus B equal to sin A cos B plus cos A sin B, and cos A plus B equal to cos A cos B minus sin A sin B. So, the same equation can be applied here. So, when we do so, we have this following equation when it is in the expanded form. Since theta star is very small, we will conclude that sin theta star equal to theta star and cos theta star equal to 1. So, applying this one, we get the equation further reduced, as you can see here. So, this cos theta star becomes 1 and sin theta star becomes theta star. Similarly, at other locations as well. So, when we further simplify, we get this equation as sigma ma equal to Pa into sin theta plus theta star cos theta plus m minus Ka square into sin theta plus theta star cos theta into cos theta minus theta star sin theta. So, again we can expand this by multiplying inside. When we do all the expansions, we get the following equation. Again we have theta star square. Since theta star is very small, theta star square will be much smaller, so we can neglect that term. So, we get this equation here, which is Pa sin theta equal to, sigma ma equal to Pa sin theta plus theta star into Pa cos theta plus m minus Ka square into sin theta cos theta minus theta star into sin square theta plus theta star into cos square theta. We reorganize the entire term as you can see below. We also know that cos square theta minus sin square theta will be cos 2 theta. Okay. So, we reorganize that and we get Pa sin theta plus m minus Ka square into sin theta cos theta minus theta star into Ka square into cos square theta minus sin square theta plus theta star into Pa cos theta. So, rearranging the terms, we have sigma ma equal to Pa sin theta plus m minus Ka square sin theta cos theta plus theta star into A into P cos theta minus Ka cos 2 theta. This now becomes equation 6. At the same time, let us look at the equation above, which is 4b. So, equation 4b is P equal to Ka cos theta minus m divided by a sin theta. So, when we multiply on both sides by a sin theta, we get Pa sin theta equal to Ka square sin theta cos theta minus m. We can further simplify this by stating that Pa sin theta plus m minus Ka square cos theta sin theta equal to 0. We can use the same thing from 4b and substitute here in 6, we get this first 3 terms to be 0. The above equation now reduces to sigma ma equal to theta star into a into p cos theta minus Ka cos 2 theta. So, here theta star is a finite quantity, it is positive value, so it cannot be 0. So, the terms inside the bracket has to be 0 in order to make sense. But to be in stable equilibrium, p cos theta minus cos 2 theta should be less than 0. For neutral equilibrium, p cos theta minus Ka cos theta equal to 0, and unstable equilibrium, p cos theta minus Ka cos 2 theta should be greater than 0. So, this defines the limit state of stability for neutral equilibrium. So, we can take this one equate to 0, p by Ka equal to cos 2 theta divided by cos theta. So, this becomes equation 8b. So, p by Ka equal to cos 2 theta divided by cos theta. Equation 4b is p by Ka equal to cos theta minus m by Ka square divided by sin theta. This is the equation of equilibrium path. Note that when m equal to 0, that is, there is no externally applied moment, p by Ka equal to cos theta, which leads to 2 equilibrium paths as can be seen in the picture below. So, we see that when we plot a graph between p by Ka and theta, we know that there is a first path which goes from 0 to p by Ka equal to 1, and then it boils down to 0 from 1.0 to at pi by 2 it reaches 0. So, basically there are 2 equilibrium paths 1 and 2 as described. 1 is the red color arrow mark and 2 is the blue color arrow mark, which is leading to 2 equilibrium paths. So, the point at which p by Ka equal to 1.0 is also known as the bifurcation point, and this type of buckling is also known as bifurcation buckling. So, if we plot with various values of m, we get the following figure on the left side. So, we plot a graph between p by Ka and theta. P by Ka is on the y-axis and theta is on the x-axis. So, here we have plotted with respect to 2 equations. First equation is 8b and the second equation is 4b. The 4b gives the equation of equilibrium paths and the 8b gives the equation of limit state of stability. So, you can see that with varying values of m by Ka, you get different values of equilibrium path as well as limit state of stability. Now, we need to study with respect to large deflection as well as small deflection. What we see on the left side is a large deflection. Previous problem, theta was assumed to be sufficiently large to contribute to cos and sin terms. This leads to large deflection theory. The deflection theta can also be assumed to be small, such that sin theta equal to theta, cos theta equal to 1. This leads to small deflection theory. So, what is small deflection theory? The equation 4b becomes p by Ka equal to cos theta minus m by Ka square into sin theta. So, when we substitute sin theta as theta and cos theta equal to 1, we get p by Ka equal to 1 minus m by Ka square divided by theta, which becomes equation 9a. So, equation 8b now becomes p by Ka equal to cos 2 theta divided by cos theta. Cos 2 theta can also be represented as 2 cos square theta minus 1 divided by cos theta. So, then when we substitute cos theta equal to 1, it becomes 2 into 1, 2, 2 minus 1, 1. So, it becomes 1 divided by cos theta again is 1. So, 1 by 1 equal to 1. So, p by Ka becomes 1. So, the equation of equilibrium path is p by Ka equal to 1 minus m by Ka square divided by theta, which is equation 9a for small deflection theory. The equation of limit state of stability p by Ka equal to 1 for small deflection theory. When we plot the same with respect to large deflection theory, we get the plot on the right side, which is the small deflection theory. Again, we plot with respect to p by Ka in the y-axis and theta on the right axis. We can see that p by Ka equal to 1 and the colors are coded in such a way that both the values on the left side and the right side are the same. So, m by Ka square equal to 0 is basically blue color, which is applicable to both the left side of the equation as well as the right side of the equation. Similarly, for the yellow color, red color as well as the green color. So, what we observe from this is that when m equal to 0, there is no change between large deflection theory and small deflection theory. Both give the same critical load. When m not equal to 0, both the theories are similar for smaller values of theta. However, for larger values of theta, small deflection theory gives excessive deflection after point A, but large deflection theory says point A is the neutral equilibrium point, denoting limit state of stability. This completes the spring bar models as well as the large deflection versus small deflection theory. We will continue our conversation on structural stability in the next class. Thank you very much.